Hi everyone, Tina here, and today I'd like to talk about projectiles. You'll usually learn about this topic during year 2 of your A-level course. I'll go through some key ideas first, and then we'll take a look at some examples. So here are the key ideas for projectiles. When you have a body moving through the air, the greatest height achieved by that body will be at the peak of that curve. The range is the distance between where it started and where it ends up. You should always consider the horizontal motion and vertical motion separately. That's really important because different things are happening horizontally and vertically. For horizontal motion, acceleration is in fact 0, which means that your initial velocity and final velocity will be the same. For vertical motion, acceleration is g, acceleration due to gravity. You can use suvat for both directions, but you'll need to do it separately. Example 1. A particle P is projected from the ground with velocity 25 meters per second at an angle of 40 degrees to the horizontal. Part A, find the greatest height of P. So first things first, we need a diagram. It's a projectile projected from the ground, so maybe something like this. Initial velocity is 25 meters per second at an angle of 40 degrees. At this point, I would write down the horizontal and vertical components of that initial velocity. So horizontally, we're going to have 25 cos 40 and vertically 25 sine 40. Part A, they want the greatest height achieved by the particle. So that will be this height here. Now we can do this by considering the vertical motion only. We take up as positive and then do a suvat. This is what we're looking for. U vertically is 25 sine 40. And then at the greatest height, the final velocity will be 0 because the particle will stop momentarily at the top before it then turns back down and falls. Acceleration due to gravity, minus 9.8 because we're taking up as positive. And then time, we don't know, but we don't care in this question. So we find the suvat equation that does not involve time, and that's this one. And we sub in our numbers to solve for s. When you solve this, you get s equal to 13.17525, which is roughly 13 meters to 2 significant figures. Part B, they want the horizontal distance traveled by P before it hits the ground. So on the diagram, that will be this distance here. Now we need to consider the vertical motion and horizontal motion separately. You can do either direction first, but I'd probably start with the vertical motion. And again, I'm going to take up as positive and do a suvat. So from start to end, the displacement vertically would actually be 0. Vertical u is still 25 sine 40. Final velocity, don't know, don't care. Acceleration, minus 9.8. And t is actually what we want to find in this case, because that's going to tell us the total time of flight of the particle. We can then sub that into the horizontal motion suvat to find the horizontal distance. So the suvat equation that doesn't involve v is this one. We sub in our numbers, rearrange to get a nice quadratic, and solve for t. When you do this, you get t equal to 0, which makes sense because that's at the beginning of the journey, or t is equal to 3.2795286 and more seconds. And that's what's going to be useful in this question, because now we can consider the horizontal motion, and going to the right can be positive here. Suvat, S is what we're really interested in. U horizontally is 25 cos 40. V would also be 25 cos 40 because horizontally acceleration is 0. And T is our time that we just found. So 3.279, etc. So once again, that T value comes from this calculation down here, where we found the total time of flight vertically. I'm going to use the suvat equation that does not involve v again here. I'm going to sub in my values and find s displacement. For the half at squared bit, I'm just going to put plus 0 because a is 0, and therefore s turns out to be 62.8066 and more, so roughly 63 meters to 2 significant figures. And that's it. Example 2. A golfer strikes a ball from ground level with velocity 35 root 3I plus 35j meters per second. Part 1. Find the initial speed of the golf ball. So first thing I'm noticing is that they want the speed rather than velocity. So that's going to be the magnitude of the initial velocity vector. Before I do any calculations, I'm just going to draw a diagram. Really important in mechanics. Projectile. This time the initial velocity is given as a vector, but that's okay. So that's 35 root 3I plus 35j. All that means is that horizontally, we've got 35 root 3, and vertically we've got 35. We don't know the angle yet, so I'm just going to label that as theta. And then for part A, part 1, I'm going to consider that initial velocity vector, 35 root 3I plus 35j. Initial speed, as we said, is going to be the magnitude of that. That's just going to be using Pythagoras to work that out, and turns out to be 70 meters per second. Part 2 wants the angle at which it's struck, so they want us to work out theta in our diagram. So I'll just draw a little vector diagram here. If that's the u vector, we know that the horizontal component is 35 root 3 and the vertical component is 35. This is theta. Looks like a nice right angled triangle, so we can do opposite adjacent hypotenuse, and we can do some trigonometry to work out theta. So in this case, tan theta is going to be opposite over adjacent. So this means theta is inverse tan of that, which works out to be 30 degrees. For part B, they want the time the golf ball spends in the air before its first bounce off the ground. So in other words, they want to know the time of flight from the beginning to that end point there when it first bounces. To do this, let's consider the vertical motion. I'm going to take up as positive and do a suvat. Vertically, S would be 0 displacement. U is 35. V, don't know, don't care. A, negative 9.8. And T is what we want. So we find the suvat equation that doesn't involve V, which is this one. We sub in our values and we solve for T. I always rearrange to get a quadratic first. You can then solve that however you wish, and you get T equal to 0 at the beginning, or T equals 50 over 7, which is roughly 7.1 seconds to two significant figures. Example 3. An ejector seat for a small aircraft is being tested and is launched from a stationary position 0.5 meters above the ground of the aircraft. The seat is fired with initial velocity 25 meters per second at an angle alpha above the horizontal, where tan alpha is 24 over 7. To pass the safety test, the ejector seat must rise at least 16 meters above the ground of the aircraft within 1 second. Determine whether the seat passes the safety test. Now, I would start with this tan alpha equals 24 over 7. In mechanics, sometimes they'll give you a ratio for the angle, and you have to do a bit of work to work out what sine and cos would be of that angle. So if tan alpha is 24 over 7, we can draw a little right angled triangle on the side, call this alpha, and that's telling us that the opposite over the adjacent is 24 over 7. We can work out what the hypotenuse is by just doing Pythagoras. So root 24 squared plus 7 squared is in fact 25. Now we can say that sine alpha will be opposite over hypotenuse, so 24 over 25. And cos alpha will be adjacent over hypotenuse, so 7 over 25. I always do that first so that it's ready to use in any calculations later. Now I want to draw a diagram, so I'm just going to read the question again and see that it's being launched from stationary 0.5 meters above the ground, initial velocity 25, angle alpha. We want the seat to rise at least 16 meters above the ground within 1 second. So in terms of a diagram, if this is the floor of the aircraft, the seat is being launched a little bit above the ground, so 0.5 meters here, and then it will be a projectile from there. Initial velocity 25, angle alpha. So this horizontal component will be 25 cos alpha, and this vertical component will be 25 sine alpha. We're interested in the vertical height here, so I'm just going to consider vertical motion, up as positive and doing suvat. Interested in how high the seat rises, so displacement. Initial velocity vertically is 25 sine alpha. Final velocity, don't know, don't care. Acceleration minus 9.8, and t is 1 from the question. Suvat equation that does not involve v is here. Sub in your values to work out s. Now u is 25 sine alpha, and we know from earlier that sine alpha is 24 over 25, and the rest we can just sub in. I'll just point out where that came from again. When we type that in, we get 19.1 meters. So that means after 1 second, the seat has risen 19.1 meters from its starting point. It's already 0.5 meters above the ground anyway. So altogether, we've got 19.1 plus 0.5, 19.6 meters above the ground. 19.6 is greater than 16, so the seat passes the safety test. Last example. A particle P is projected from a point O with velocity u meters per second at an angle of theta to the horizontal. When P has moved a horizontal distance x, its height above O is y. Part A, show that this equation is true. Now this can look a little bit intimidating, but do not let the complicated algebra put you off. In projectiles, we're still just going to consider the vertical motion and horizontal motion separately. Now I've already drawn the diagram for this one, and I just wanted to point out what x and y are really talking about. It's basically just saying that anywhere along the flight path of that projectile, you can describe the particle's position as a coordinate x, y. So for this question, we're just working with generic variables. We're not actually given any numbers yet for part A. So projectiles, let's start with vertical motion. Again, you can start with either, but I'll just start with vertical here. I'm going to take up as positive and do a suvat. Vertically, displacement is described as y. Initial velocity will be u sine theta from the diagram. Final velocity, don't know, don't care. Acceleration minus g. Now I'm going to keep it as minus g rather than minus 9.8 because I can see that there's a g in the equation that I'm trying to get to. Now, the interesting part here is that we can keep t as a generic t variable, time variable, and that's going to be the variable that links the vertical and horizontal motion together. Because at this moment in time, when the particle is here, let's say, at x, y, time is t. The same amount of time has passed, no matter whether you're thinking about vertical or horizontal motion. Let's see what we get when we sub in these values into a suvat equation. So using this one, we get this. You can simplify this a little bit to get this. And that's as far as I would go with that one for now. Next, I'll think about horizontal motion, going to the right as positive. Another suvat. Horizontally, displacement is x, and initial velocity is u cos theta now. Final velocity stays the same horizontally because a is 0 and t is still t, same time as the vertical motion. Once again, the t links the two motions together. If we use suvat for this direction, we get this. Just going to put 0 because a is 0. And then we can rearrange this for t to get t is equal to x over u cos theta. That's helpful because now we can take this t value and sub it into the t that we had from up here. We can do that because time is t for both. When you sub this t value into the y equation, you get this. Now we can look for things to cancel and simplify. So I can see there's a u there and a u underneath, which will cancel out. This will then become x sine theta over cos theta minus g over 2, and then I'll probably just expand that squared bracket to get this. Now, because sine over cos is tan, that means we get x tan theta minus gx squared over 2u squared cos squared theta as required. B. Given that theta is 45 degrees and that when x equals 6, y equals 2, find the speed of p at the point where x equals 6 and y equals 2. So now if we look at the diagram again, we can replace the x and y with these specific x and y values, so 6 and 2. And they want the speed at that point. Speed will be the magnitude of the final velocity. And I'd be thinking about final velocity as a vector here, because it clearly has a direction. Now, before we can find v, we should probably work out u using the equation from part A. So let's sub in all the values we're given into that first equation. So that's going to look like 2 equals 6 tan 45 minus g times 6 squared over 2u squared cos squared 45. If you tidy this up a bit, you get this. You can then rearrange it, work out that u squared is 9g, means u is going to be plus or minus 3 root g. We're going to take the positive version, because when we worked this out in part A, we took up to be positive, as per the diagram. Now we can look to work out v. So to do that, let's consider the vertical motion and do a suvat. So up is positive, v is what we want in this case. We now know that u is 3 root g sine 45, because for the vertical motion, we're just interested in the vertical component. A is minus 9.8. Now it looks like we don't know s or t, but the good news is we can actually work out what t is from using an equation we found in part A for t. In part A, we had that t was equal to x over u cos theta. So if we sub our values into here, we get 6 over 3 root g cos 45 which works out to be 2 root 10 over 7. And that we can then use in our SUVAT. We don't need S. We can look for a SUVAT equation that doesn't involve S, which is here, and then we can work out V. So according to this, V will be equal to 3 root G sine 45 plus minus 9.8 times 2 root 10 over 7. Works out to be minus 7 root 10 over 10 meters per second. Now it's okay that it's minus, that just means that vertically the velocity is going down at that point. Let's now consider horizontal motion. Going to the right is positive, and also remembering that U is equal to V in this case. So because we know that the initial and final velocity will be the same horizontally, don't need to bother doing a SUVAT, you can just say that V will be equal to U horizontally, which is 3 root G cos 45. Works out to be 21 root 10 over 10. Now we know that speed is going to be the magnitude of our final velocity. So I'll just draw a little picture of what that velocity vector is looking like now. We found the horizontal component of it to be 21 root 10 over 10, and the vertical component going down, because it was minus, as 7 root 10 over 10. So all that's left to do is a Pythagoras to get the magnitude. When you do this, you get a surprisingly nice answer of 7 meters per second, and we're finished. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else who you think might find it helpful. Thanks, and see you next time.